Yeah, good morning. Everybody awake? Is there a need to discuss the German soccer team or no? Well, they made it, right? It's good that a soccer match lasts for 95 minutes, right? I mean, this is good. But so today, what we have seen is a logic LTL, and there what we know is that the main operators, let's say from the apart from the propositional logic stuff, is next. So we have next of a formula, and we can write down phi1 until phi2. What is good about LTL is that you can have arbitrary nesting, right? So you can, for instance, write down formulas like eventually always A, or you can even write things down like it's the case that A holds until eventually always B. I mean, so you can nest these kind of operators inside an until formula, etc. Yeah? Good. The logic that we have seen, and this is interpreted over linear sequences. Yeah? So linear sequences, traces. And then in the last lecture we have seen a logic CTL. And the main difference with LTL and CTL is no longer we are going to interpret the formulas over traces, but we're going to interpret things over what they call computation trees. And these are infinite trees. And the kind of operators that we have is, apart from the propositional logical things, is that we now have state formulas. So state formulas are of the form like a proposition holds, or a conjunction holds, or a negation holds. But in particular, you can write down things like for all parts starting in a certain state, a property phi holds. And you can write down things like there exists a path such that the property phi holds. And then we have path formulas. And these path formulas are of the form next. But now, in contrast to LTL, it's not next with an arbitrary path formula or an arbitrary formula, but it's in contrast. This is a state formula. Whereas the path formulas are of the form, so I call this phi and I call this capital Phi. Yeah? And you can write down things like phi1 until phi2. Good. So we see the syntax is different. You can talk about all computation paths. You can talk about the existence of a computation path. You can nest certain things. So for instance, things that you can write down in CTL is for all paths, it's always the case that there exists a possibility to go back to the initial state. So you see that you have the possibility to nest, let's say, an existential quantification inside a universal quantification. On the other hand, you're not so liberal anymore, like here, because things that, if you would like to write down something like this, then we should write down something like for all paths, or there exists a path, A until, and now the syntax forces us here to put a state formula. And that means, again, we need to be forced to put something like a universal or a existential quantification, so the obvious way to write something now down would be something like this. Yeah? No, that would be a guess. Yeah? So we see that we are less liberal in nesting these, what I call temporal operators, like until, box, diamond, and so forth. But on the other hand, we have the flexibility to nest these things. And that leads to the following effect, and that's what we're going to study today in detail. So if you look at all the formulas that you can express in CTL, or all properties, and you look at all properties that you can express in LTL, then what we're going to see is that they have a common fragment. This is not so strange. I mean, I can write down things like A and B in all logics, right? That's obvious. So there is a common fragment. That's not empty. But in particular, there are also formulas in LTL that you cannot express in CTL, and vice versa. So one example that can express an LTL is something like eventually box A. We're going to see today that you cannot express an equivalent property in CTL. First, we need to make sure what equivalent exactly means, but for the moment, we assume that there is not the case. And similarly, here we have formulas that you can express in CTL that we cannot express in LTL. And one of the examples is already on the board. It's for all box there exist eventually, no, initial. Yeah. Good. So the question is how to prove this, and in particular, why is this the case? So that's the topic of today, expressiveness of CTL versus LTL. Good. So the first thing we're going to define in order to be able to compare the two logics is that we need to make sure what does equivalence actually mean. Actually what we are going to do is we're going to define an equivalence between a CTL and an LTL formula, and we do this on the level of state formula. So we take a state formula, capital phi, and we take an LTL formula, phi. And then we say that the CTL formula, state formula, capital phi, is equivalent to the LTL formula phi, if and only if, now intuitively speaking, you cannot find a transition system for which one formula holds and the other one doesn't. Yeah. So that means for all transition systems and all states, if a state S in that transition system satisfies the CTL state formula phi, and that of course has to be is defined in terms of the semantics of CTL, if and only if that state satisfies under the LTL semantics the LTL formula phi. Okay? So as I said, intuitively speaking, there is no, you cannot distinguish these two formulas by finding a state for which one formula holds and the other one doesn't. Good. So obvious cases are things like this. Atomic propositions, clear. For all next A. No? Why is this the case? Well, this means that for all parts next A holds. If you now go to the LTL formula next A, this holds in a certain state S if next A holds, but that has been defined in terms of for all parts starting in S, next A holds. And that's exactly what is written down here on the left-hand side. So what you see is here the universal quantification is part of the syntax of the logic. In LTL, if you look at the state and you look at an LTL formula, a universal quantification is implicit because it's in the semantics. Yeah? A state satisfies an LTL formula if and only if for all parts starting there it satisfies the formula. This has been our definition of the semantics. Yeah? So you see there is a difference between syntax on the one hand side and the semantics there. The same with A until B, similar reasoning. For all parts A holds until B becomes true. This LTL formula A until B, if you interpret this in a state, exactly means the same. For all parts starting in that state A until B holds. Good. That things are not so easy, I like to show by means of an example. And the example I like to discuss is the following. So LTL versus CTL. So I want to look at the formula eventually next A. So eventually next A is in LTL. So I write this down like this, which means according to the semantics of LTL, this formula on the left will be equivalent to the formula on the right. That means you can swap the two modalities. I hope this is not a big deal to see that this is the case. Yeah. So eventually you say, well, there is a next state where A holds, and that's the same as saying, well, from the next state on, eventually I will in A, C, and A. Yeah? So you can swap the two things. But this doesn't hold. If you now would look at what intuitively you would think what is a similar CTL formula would be something of the form for all eventually, right? Because we have seen in the previous slide, you just put a for all eventually, for all in front of it. And then you say something like for all next A. This is not equivalent under CTL to if you would take the formula on the right and do the same thing. So what I did is I inserted a universal quantification here and I did it at the front. My previous slide said at the front. That's basically the same as in LTL. What now I also do is there. Yeah? Because what we have is we have that next eventually A is going to be equivalent with for all next for all eventually A. So the two right-hand sides, this formula and that formula are equivalent, but the two left-hand sides are not. So we have eventually next A is not equivalent to for all eventually for all next A. Good. So example, here is a transition system. And suppose this is the following transition system. So this is state 0, state 2. So then there also should be a state 1, right? This is labeled with A. This is state 1. This is state 3. And this has a self loop. And we start in 0. Right. Okay. Claim. TS satisfies the formula for all next for all eventually A. How can we see this? All states satisfy next for all eventually A. Yeah. I mean, just pick a state, this one, claim. This satisfies next, next for all eventually A, which means this is eventually A, and whether you go there, you eventually get an A. Yeah. The same here. You can only go to the right. The same there. You can only take the self loop, and the same here. Yeah. No matter whether you go back or no matter whether you go there, you get for all, I mean, eventually this. Thus, in particular, we have that state 0 satisfies for all eventually A. But TS does not satisfy the formula where we swap the two modalities. Yeah. Why is this? Well, we're going to look at the innermost formula. So what's the satisfiability set of this formula? Just for you remember, this was the set of states satisfying this formula. This is for all paths next A holds. For which states in this transition system is this satisfied? Well, only for 3. Yeah, that's the only state that satisfies that for all paths next A holds. Not for this one, yeah, not for that one. There is a possibility that the next path has A, but you can also move to the right. Yeah. So this state does not satisfy for all next A. And that means that you can simplify the formula. So now we can look at the formula. So now you have that S0 does not satisfy for all eventually S3. Yeah, so what I do here is I replace this part of the formula with 3. Well, I should write down 3 here. Yeah, and this is clear. For 2 it also holds. Very good. Yes, absolutely. The good thing is it doesn't spoil my argument, but you're absolutely right. Yeah. 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 So I should write down here 2 or 3. Yeah. But this is still true because you can also move to the left. Yeah. And for instance, you can cycle around infinitely often here, and then you don't have eventually 2 or 3. Good. So TS violates this formula for all eventually for all next A. Good. So what I showed you is indeed that these two formulas, that this holds. The way to show this is give a counterexample. Give one transition system for which one formula holds and the other one doesn't. Yeah? And this is one counterexample. Good. My challenge is always to promise you a bottle of beer if you can find smaller counterexamples. Right, so this lecture will be full of counterexamples. I'm very much interested in finding smaller counterexamples. Yeah. Good. Good. So what we have learned is, yeah, things are not that easy in the sense that you cannot just take this LTL formula and, for instance, this is an equivalence in LTL, but a similar equivalence in CTL doesn't hold. So you have to be a bit careful. Yeah? Things are more subtle than this, as we're going to see. Any questions so far? No? Good. Good, so here are more examples. So the CTL formula is on the left, the LTL formula is on the right. And what you've seen is very simple. There is no nested modality, that's the important point. There is no nested, eventually boxed, eventually until or whatever. It's just one modality here in the LTL formula. And what you can do then is that you can prefix this universal quantification, because as what I mentioned before, here the universal quantification is in the syntax, here it's in the semantics. Yeah? So this should, I hope, not be too much of a surprise. The nasty things happen with nesting. This is also not nested, this is all fine, so unless is fine. This is an interesting thing. So this works, and let me see why this works. So we can maybe provide some argument about this. Because this is a nested modality, right? So why is this correct? So how would you show this? So I want to show that for all box for all eventually A is equivalent to box eventually A. I think there was an intuitive argument already on the slides of the previous lecture, but now I would like to do this more in a more rigid way. So this is what I want to prove. Yeah, so what we want to prove is the following. S satisfies the CTL formula if and only if for all parts in S it is the case that pi I, this part pi at position I, satisfies A for infinitely many I. Good. So how would you show this? We're going to show this equivalence by looking at the implication in both directions. So we're going to look at the implication from left to right. Let S satisfy this CTL formula. Good. Then we take a part starting, and this S0 is exactly S, so that's a part and starting from S. And we take some index at least 0. Then it follows that pi satisfies box for all eventually A. Yeah, because the state satisfies for all parts, so if I now pick an arbitrary part, that part satisfies the rest with stripping off this first quantification. Good. In particular, we have that Sj, which is one of the states in pi, then satisfies for all eventually A. So basically what I'm doing, and I like to stress this, is, and that's because that's typical in these kind of proofs, you look at this CTL formula, and then you now start reasoning from the front to the end. So not like we did in the examples of a transition system, because then we were looking first at the innermost formula. We were trying to see which states satisfy this, and then we were reasoning from inside out, intuitively speaking. Now we reason from outside in. Yeah? So I strip off this first thing, so I pick a part. Well, this is a part starting in S, so it satisfies the remaining formula. So this simplifies the formula to this form. yeah, then I know that this part has this shape. This is a box, so I pick a certain state at index j, so that j satisfies this formula. Yeah? So that makes life already a little bit easier. Yeah? So now I have this as j, and now you have take this 4. If you take the part starting from j, which is something of the form sj, sj plus 1, sj plus 2, etc. Yeah, this is a member of the parts starting at j. We have that part satisfies eventually A. Thus, SE satisfies A for some I at least j. No? Again, I simplify the formula. Thus, SE satisfies A for some, that's already what I wrote down, sorry. As this applies to every j, yeah, every j because of this box, it follows pi I satisfies A for infinitely many I. Yeah. Good. So what you see is that this formula we started with, then we simplified it to this, then we simplified it to this, then we simplified it to this, and then we reason in the other direction. Yeah? That's the way to deal with this. So this is one direction. So let's see about the other direction. Good. Let pi be a part starting in S. So say pi is S0, S1, S2, etc., where this equals S. Good. To show that S satisfies for all box for all eventually A, we have to prove that pi satisfies box for all eventually A, and that means we have to prove that Sj satisfies for all eventually A, and this holds for all j at least 0. So again, I do a similar reasoning as before. I look at the CTL formula, I pick a part, this strips off the first quantifier, then I look at this formula here, and then I start reasoning about what does it mean for this part, and then I say, okay, S for all Sj, you need to satisfy this formula. So this is the proof obligation. Yeah. Good. Let j be at least 0 and take pi prime to be a part Sj prime, Sj plus 1 prime, Sj plus 2 prime, etc., being a part in Sj. So this state here equals Sj. No. What I'm doing is basically I take two parts. So if this part is orange, S0, S1, S2, etc. Yeah, this doesn't necessarily need to be the same part. That's important. Do I have any other? Blue, right? So this is another part, Sj prime, Sj plus 1 prime, Sj plus 2, etc. Yeah? So I have an orange part, and then from Sj on has the possibility to continue with this blue part. Good. To show that Sj satisfies for all eventually A. It suffices to show that pi prime, this blue part, satisfies eventually A. Good. Take pi double prime. And now I'm going to mix the two parts. I'm going to start with S0, etc., up to Sj. And then I continue with the blue thing. Yeah. So in terms of a tree, what I'm doing is here is the tree. Yeah. Now I look at all computations, so I look at pi. Let's suppose that the initial state was S0. Now I look at the part pi, which was orange. Do I still have orange somewhere? Yes. So I have some orange part. This orange part is here. Now I take some state Sj. And because this holds for all, it doesn't matter which one I take. So I take an arbitrary Sj. And now I say, okay, look at the part that starts from Sj, but maybe goes in a different direction. Yeah? This is what we're going to do. Now this new part that we consider, the prefix being orange, the suffix being blue, of course is also a part starting in the root, so it also satisfies this formula that we started with, right? So it assumes, we know that there are infinitely many A's along this path, because that's the assumption, yeah? So in particular, this means that somewhere on this blue suffix, there needs to be an A somewhere. Yeah? So this pi prime is a part, right, starting in the root. Yeah? That's the way I constructed it. Yeah, okay. So here you're absolutely right. What I should write down is do this, because this Sj prime is exactly Sj. Yeah. Wow, you're awake this morning. Very good. Yeah, absolutely. You're not allowed to stutter in that state. You should move on. Yeah. That was also my intention, but yeah, it is also here on the paper. It starts with j plus 1, not with j. Exactly. So by assumption, as I already mentioned, pi prime double prime visits infinitely many A's, infinitely many times an A state. Thus, there exists an I at least j such that Sj prime, which is on the, and now I should be careful, I prime, yeah. It's the I state that I'm reasoning about, satisfies A. Exactly. Good. Thus, pi prime satisfies eventually A. As this holds for every pi double prime, I've taken an arbitrary blue suffix. I could have taken another suffix. Same reasoning applies, right? We have that Sj satisfies for all eventually A. Yeah? Take another prefix, or suffix, sorry, let's make it purple. So suppose there is another suffix which is purple, same reasoning applies. This also needs at some point to visit an A state. Yeah? And this holds for all suffixes starting from Sj. Yeah? So the reason is, I mean, I just took an arbitrary one, and that, of course, is enough. Thus, and this holds Sj for all j. Thus, pi satisfies box for all eventually a. Thus, S0 or S satisfies for all box for all eventually a. So here we have seen an example of a nested formula, a formula which has a nested modality in LTL. And that means, as written down as on the slide, these two formulas are equivalent. Yeah. And this may now lead to the idea to squeeze in universal quantification before every modality, and that's not the case, as we already have seen with the next and eventually. There we cannot just swap the two modalities. Good. So both formulas mean infinitely often A. So if I want to express infinitely often A in CTL, I can use this formula. Why is this helpful? Because this is unconditional fairness. Yeah, so this is important because this formula is now unconditional fairness. So we just have proven that you can express unconditional fairness in CTL. Good. But this is not a general recipe, as we already have seen with the next. But if I swap the box and the diamond modalities, so rather than writing down box diamond, I write down diamond box, we're going to see that this is not equivalent to the formula where we put a universal quantification in front and between the diamond and the box. These two formulas will be not equivalent, as we're going to see in a minute. Good. So here is the CTL formula for all, eventually for all box. So what does that mean? This formula says true in a certain state if on every path starting in that state S, there is a state T, and this T satisfies for all paths box A. So all states in the whole computation tree of T, so if you would draw a tree, and if you would look at the subtree rooted at T, the whole subtree is blue. That's what this formula says. For all paths, eventually I can reach the root of a tree which is completely blue. So this is an example of a transition system where this holds. Here is the initial state. So this is S. No matter in which direction you go, at some point you reach a root of a subtree and the whole subtree is blue. Or you go here and then here, assuming that the whole thing underneath is blue as well, the whole subtree is blue. Good. So here is a transition system satisfying this formula. No matter where you go starting from the initial state, you can either move to the left, but then you get stuck in that state. And that means in terms of the computation tree, this will be an infinite chain, which is completely blue. The other possibility is to get stuck in this strongly connected component. And that means that you simply have in the computation tree also a chain of A's here. Good. We're going to show that this LTL formula is inequivalent to that CTL formula. So to prove that this is the case, what we're going to do is to find a counterexample. So we find a counterexample, a transition system such that, for instance, it satisfies the LTL formula and not the CTL formula, or vice versa. Good. So we're going to see an example that satisfies eventually box A, but not the CTL formula. Good. So this is the example of a transition system. Just 3 states. The middle state is yellow. The other 2 are just blue states equipped with a self loop. claim this transition system satisfies the LTL formula eventually box A. Now, how can we check this? We have only one initial state. There are two possible computations. You take this cycle 0 or more times, and then you move to the right. Yeah? This eventually always satisfies A because you get into this state and this box A. The other computation stays here infinitely often, but that also trivially satisfies eventually box A. Good. It doesn't satisfy the CTL formula for all parts eventually for all box A. Now, one way to see this is to look at the computation tree. So if we look at this transition system, you can build the computation tree, which looks as follows. This corresponds to the initial state here on the left, and now there is a branching between either taking the self loop, which means going to the left, or going to the yellow state, which means to the right. And it's obvious, I hope, that once you have reached the yellow state, the only thing you can do is moving to the right, and that means you go up into this sequence of A's. Yeah? This means take the self loop once, and there again, as before, you have the choice between either moving to the yellow state and ending up with a chain of A's, or chain of blue states, or you move to the left. Yeah? Good, so that's the computation tree. Now we're going to look at, remember, from inside out, which states satisfy the innermost formula. The innermost formula says for all parts, always A holds. Yeah? Good, that only is applicable to this state over here. Yeah? Because there's only one computation. This computation always stays there, so that satisfies box A, and therefore the state satisfies for all computations box A. This state doesn't satisfy the formula because it is not blue. That state doesn't satisfy the formula because there is a possibility to move to the right, and that would violate being blue. Yeah? Good, so the only state satisfying this formula is the green state. So we can, so we can simplify this formula for all eventually green. Now this is true if you move here, it's true there, but if you take the self cycle, yeah, so if you take this loop, then you are not going eventually to the green state. And therefore the initial state does not satisfy the formula for all eventually green. And therefore the transition system doesn't satisfy the formula. Good. So the recipe to show that two formulas are inequivalent is to find a counterexample. Now this is like searching in the whole space of all possible counterexamples. There are infinitely many, so that's not that easy. But there is maybe a somewhat helpful theorem. And this says the following: for each CTL formula, state formula phi, the following holds. Either there is no equivalent LTL formula, or the CTL formula is equivalent to an LTL formula, which I can construct by just removing all the part quantifiers in phi. Okay? So let's apply this to the two examples we have just seen. This theorem is due to Dragicescu and Clark somewhere in the 80s. The first remark is it goes in one direction. You start with a CTL formula. You want to show, does there exist an equivalent LTL formula? So let's start. You start with a formula that says for all box for all eventually A. That's the formula in CTL. This is phi. Now you strip out all the quantifiers. So that gives you the LTL formula box eventually A. Yeah. So this is my LTL formula phi. Now the theorem says the following. Now there are only two possibilities, right? Either phi is equivalent to this formula. Now this is what we just have proven actually, because that's exactly the example we just have proven. So this theorem does not is a replacement of the proof obligation. You still have to prove this. But if this turns out to be not the case, so if you can find me a counterexample, right, you don't have to look any further for any other LTL formula. So either this holds or, and that's the part, there is no LTL formula. Yeah? That is equivalent to phi. And that's second part is the strength of this theorem. Yeah? So the first thing to do is you give me a CTL formula. Yeah? So in this case, you can prove this, which is still for us a proof obligation because we have to prove that this equivalence holds, what we just have seen. If you now take the other example, for all, eventually for all box A, same trick, remove the quantifiers. The quantifier said this is eventually box A. Yeah? Either these two formulas are equivalent, or, yeah, there is no equivalent formula. Good. We just have seen that this is not the case. Yeah, my counterexample of the three states. So what we just have shown by means of this theorem, there is no LTL equivalent formula to this CTL formula. Yeah, so in the Venn diagram, if this was CTL and this is LTL, this is an example of a formula, namely that's exactly this one for all, eventually for all box A, is a CTL formula for which there does not exist any corresponding LTL formula. Yeah, and that's the strength of this theorem. So still there is the obligation to show that this is the case. Finding the counterexample is not simplified, but if you, let's say, have one counterexample, then there is a very strong conclusion. You don't have to look any further for any other LTL formula that might be equivalent, because it doesn't exist. Good, what I just wrote down, I think it's also somewhere on the slides, but yeah, okay. Yeah, so let's skip this. So what I'm going to show is this formula. And again, all these formulas are nested. That's the whole thing. For all parts, eventually I can reach an A state, and all its direct successors also satisfy A. That's what this property says. So what we are going to do is do the trick, remove the quantifiers. So this gives us immediately this LTL formula. Now there are two options according to the theorem. Either this formula is equivalent to that formula, so we prove this, or we provide a counterexample, and then the conclusion is you cannot express this property in LTL. Good, and actually we're going to see that this is indeed the case. This is not equivalent, so we have to find a counterexample. I will show you that in the next slide. Conclusion, by the theorem, there is no LTL formula equivalent to this formula. So again, what does this formula tell you? It tells you the following. You have a computation tree. It says for all parts, so take a part, eventually, somewhere here, you reach an A state. Yeah. And that A state has a specific property. Namely, all its direct successors are also satisfying A. In particular, the direct successor that is on the same path, but all its neighbors as well. Yeah, his brothers and his sisters, that means also the one that moves here is an A. Yeah, that one that moves here is an A state. So it's, yeah, a kind of a branching to only A states. Yeah. And this property of this branching, and that's exactly the idea why we look at trees and not at sequences, you cannot express in LTL. And the real core reason for this is there you can only reason about sequences and not longer about this branching thing, which is the key strength of CTL. Good, so claim these two formulas are inequivalent. How are we going to show you this? By means of a counterexample. Good. So we're going to show a transition system that satisfies one of the formulas, for instance the LTL formula, but not the CTL formula, or vice versa. And the claim is that this example is one way to show this. So initially we have the possibility to move to the right and go to yellow and then only be blue, or the other one is mirrored in the sense that this is blue and then we only stick to yellow states. Yeah? Good. Claim, this satisfies the LTL formula eventually A and next A. Now let's check this. You start here, there are two options, you go left or you go right. So let's go left. Left means eventually, namely here, you're already in a blue state and the next successor is blue, so moving to the left definitely satisfies A and next A. Eventually A and next A. Now the other option is moving to the right. Yeah, moving to the right means, okay, this is an A state, but its successor is not. So that doesn't work, but you get to here, this satisfies A and its direct successor is also satisfying A. So both paths satisfy this property. Okay? Good. And that's written down here. You can either move to the left, this is this, and then you get this trace where you have 2 times A in a row, or you go to the right and then you have 2 times A in a row here once you are in this state, which I just explained. But it doesn't satisfy the CTL formula. Why is this not the case? Well, just reason again from inside out. So we're first going to look at this subformula. A and all direct successors are A. So which states are blue and only have neighbors or direct successors which are also blue? Well, this is not the case for this state, because it only has one neighbor which is yellow. It's not the case for this state because it has at least, it has one neighbor which is yellow, but it's true for that state because its only neighbor is itself, and that's blue. So this means for all eventually S4. And now you immediately see this is not the case because I can initially decide to move to the left. Yeah? I can move here, and then of course I never reach S4. Yeah? So this computation, S0, S1, S2, does not satisfy this formula. Yeah? Good. What's the point? The point is that this path is violating this formula, but in order to reason about this, I have to reason about this successor, which is not on the path, but which actually spoils the fact that I'm satisfying this property. Eventually, I reach an A state which only has direct A neighbors. This is the A state. This is the way I go, and that's definitely satisfying blue, but there is also a possibility that I don't take, but that's actually now spoiling my argument that it's a direct neighbor which is not blue. Okay? Any questions? No? Good. So, expressive powers of LTL and CTL are incomparable. Well, that's not exactly what we showed so far. We only have seen a couple of examples in CTL that we cannot express in LTL, not yet the other way around. That will come. Yeah? And that's a bit harder to prove. So we have seen these formulas. Actually, we have seen this example, we have seen that example, and I'm going to show you actually direct proof of this example, which is simpler than finding a counterexample. And what we are going to show as well is that this LTL formula has no equivalent CTL formula. Notice here the theorem that we have seen is not applicable. The theorem says, give me a CTL formula, eliminate all the path quantifiers. Either you get something, well, you definitely get an LTL formula, but either this LTL formula is equivalent to the CTL formula or there doesn't exist any equivalent one. But it's not useful for this direction. Good. So this is the picture that was already a couple of times on the board. So this is a property that is expressible in both because we have seen you can squeeze in a universal quantification at the front and here in between the box and diamond, and it gives you the same, equivalent formula. This is a formula, and that's a formula that we just have seen that there is no equivalent LTL formula. This is what I'm going to show in a minute, and that's what we're going to show in 5 minutes. Yeah. Good. Good, and in particular, this has some consequences for, in particular, strong fairness. Yeah. Why is this? So let me spend some words on this word strong fairness on the slide. So we have seen unconditional fairness can be expressed because that's exactly the formula which is in the intersection of the two, right? Infinitely often do something, unconditional fairness. What about strong fairness? What is strong fairness? In LTL, I would express something like something is infinitely often enabled, then I take something infinitely often. So something of the form infinitely often A, enabled, then infinitely often I take something, do something. Good. Now what we know is that box eventually A is equivalent to for all box for all eventually A. Yeah. But this formula, phi, phi is not equivalent to replacing just the first formula by this and the second formula by this, because you have to take the implication into account. Yeah, what I did is I replaced this one by an equivalent one and that one by an equivalent one. But that's not the way it works, because you have to take, as I mentioned, the implication into account. Because phi is equivalent, logically, to saying not eventually A or, that's the implication. Well, that's equivalent to pushing the negation inside, eventually box not A, or infinitely often B. Yeah? What's the problem? Well, this is the problem. Because we just have seen that eventually box something cannot be expressed in CTL. So this cannot be expressed in CTL. So this means strong fairness cannot be expressed in CTL. And maybe you're tempted to say weak fairness cannot be expressed because weak fairness is something of the form, maybe you remember weak. What was weak fairness? Weak fairness was something on the form, from some point on continuously something is enabled and then you take something infinitely often. Yeah? But because of this, you have taken negation, etc., and then you get something that you can express. So this is not the problem, it's the strong fairness which is the problem. Good. First part, last thing that I still owe you to show is that this formula has no equivalent LTL formula. Of course, I could try to do the same scheme as before. Remove the quantifiers, find the transition system for which the LTL formula is satisfied, but the CTL formula is not. Home exercise. You can also provide a direct proof, and that's what we're going to do now. So we're going to put a direct proof. There is no LTL formula equivalent to this CTL formula. What's the reasoning? We try to find an argument by contraposition. Okay? So in order to get a contradiction, I'm going to assume that there is an LTL formula that is equivalent to the CTL formula. I don't need to know how this formula looks like. I just assume there is an LTL formula phi, and this guy is equivalent to the CTL formula. Good. Now we consider a transition system, and this transition system is very simple, just two states, a yellow state and a blue state. Claim the set of states satisfying eventually, there exists a path, eventually A, so I'm going to look at the innermost subformula, same scheme as before. Well, this definitely holds for T, and it also holds for S because you can move to the right. But that means that the transition system satisfies this formula, so because for all paths, for every state you are, because all states satisfy this subformula, every path satisfies this subformula. Agree? Or any disagreements on this? No? Good. Okay. But by assumption, that also means that it satisfies the same LTL formula, right? Because the LTL formula, by assumption, was equivalent to the CTL formula. Good. That makes sense? Yeah? Good. Now I consider this transition system, which I obtain from the first one by just removing the blue state. Okay? Good. Argument as follows. The traces of this transition system, it only has one trace, namely you can only infinitely loop here, is a subset of the traces of the original one. Obviously, because I just deleted one state. Yeah? By assumption, right, T1 satisfies the LTL formula, which means all the traces in T1 satisfy this formula. Now I give you a transition system which has less traces. So this also satisfies this formula. Yeah, that's the property of LTL. Yeah, so this satisfies the LTL formula. But that means that this transition system satisfies phi, but of course it doesn't satisfy the CTL formula. Yeah? I mean, by assumption phi is equivalent to this formula, but that's a contradiction because this doesn't satisfy this formula, because it doesn't even have a blue state. Yeah? Good. As I said, this is an example of a direct proof. An alternative way of proving this is take the CTL formula, remove the quantifiers, give me an example for which one formula holds and the other one does not. Yeah? That proof possibility is not vanished. This is an alternative proof, and this is a very neat proof, to my opinion, to show you this. Okay, so this gives me a contradiction. Okay, so that's what we have seen. What is left is this part, namely this LTL formula, that's the claim. There does not exist an equivalent CTL formula for this. Good. This is somewhat harder. So we're going to look at this formula. Claim there is no CTL formula that is equivalent to this guy. What's the sketch? The sketch of the proof is as follows. So I'm going to build two sequences of transition systems. So let's first look at one sequence. So this is a sequence Tn, and it's just a natural number. So I'm going to consider a sequence T1, T2, T3, T4, etc. of transition systems. And then I'm going to build a very similar but slightly different sequence, namely T prime 1, T prime 2, T prime 2, 3, etc. Yeah. Such that for all n, we're going to see that this first transition system, for every n, every element of the first sequence violates the LTL property, whereas the other one satisfies the LTL property. Good. Then we're going to argue, I'm not going to prove this, but you can prove this by means of induction, that they satisfy the same CTL formulas of length at most n. Good. So let's first look at the two transition systems. Good. So we start the two sequences in parallel. The sequence here, and that's the first element of the second sequence. And the first element already shows you the difference, and that will be the only difference. So we start here in a state that doesn't satisfy A. It can move to this A state, it has a self loop, but it can move back. That's the key point. That's the whole key point. This one is a copy of this guy, but this going back option has been removed. And now we're going to extend this. So here is T1. So first go back to the, maybe we write it down on the board so that you can see what we are doing. So the idea is that Tn does not satisfy for all box A, and T prime n satisfies for all box A. Good. Let's first look at T0. Yeah, and check this condition for 0. So claim, yeah, this does not satisfy for all box A, obviously because of this back option. This one doesn't have this back option, and indeed for all paths eventually you get box A. Good, clear. So now how are we going to extend this? This is T1. I take T0, this is T0, and I extend it by a state not satisfying A, and then again having this sink where I'm stuck. Good. Let us check this condition. It violates this eventually box A. Why? Well, because of the same reason as before, because of this back option. Yeah? That's the point. You can just cycle around here, or cycle around, take this cycle finitely many times, but this option going back spoils the fact that you have a computation that is not always satisfying A. Clear? Good. Here I do the same. I take the T0 prime, which is the first part, and I extend it with this state and with that state. So I extend it in the same way as that. Yeah? Still, that's one satisfies eventually box A. Good. Now I can build T2. So this is, I hope you find this scheme. This is T2. You take T1 and you extend it with those two states. Yeah? Same as before, you violate this property. And in the same way, I get T prime 2 by just not having this back option. Good. So I have this sequence of those things. Okay? Good. One satisfies the CTL, LTL formula, the other one does not. And now the point is that, so that's what we just have argued. So this is the way they constructed it. So Tn is basically this prefix with this going back option and then followed by T prime n minus 1, and the same with Tn prime. That's the same as this prefix and then followed by that one. Basically saying the suffix of these two things is basically always the same. Good. But now the point is, for all CTL formulas of a certain length, Sn, so this state, satisfies this formula if and only if S prime n satisfies the same state. And the same for Tn. That means you cannot find a CTL formula that distinguishes the two transition systems. The sequence is size n. You cannot find a CTL formula of size n that distinguishes the two. Yeah? And the way to view that is the following. Maybe we look at one example. I thought I had it written down, right? So maybe we look at one example. Because of course it should be possible to distinguish the two because of this back option, but you need quite a pretty long formula to capture this. The way to prove this is by induction on the structure of CTL formulas of size n. So the example I'm going to show you is T1 and T1 prime. Yeah, let's just draw them. So this is empty set. Then here we have a state A. We have a self loop. We can move here and we can move back. That's the important point. We can here move to the empty set, and then we can move to a state A, and we have the self loop. That's T1. And then we have T1 prime. This is basically a copy, but this only has this option. Good. Okay, let's assume the only atomic propositions are A. So the way to classify this state that has this empty set is by the formula not A. Then it's clear that you have a trace in T1, right? So you can take a trace like something like this. So that's a distinguishing feature. I go here, I go there, I go once back. So I go here, here, I go there, I go once back, I go here, I go there, and then I move there. This once going back is the crucial thing. Now I would like to capture this once going back by means of a CTL formula. Okay? So my claim is the shortest CTL formula that distinguishes those two transition systems is as follows. I write it down and then let's try to explain this. So T1 satisfies the formula. There exists next A and there exists a next not A and there exists a next A and there exists a next not A. And now you have to close all the brackets. 1, 2, 3. Is that all? I have more here, but let's see, an A, and there exists a next not A, and there exists a next A, and there exists a next A. Yeah, seems to be okay. This. Yeah. Okay. Claim this is satisfied by T1, but not by T1 prime. So this guy has a next state which satisfies A, and that state has a next state which doesn't satisfy A, but who has an A successor, and there has an exists next A. So the possibility to go back is captured by this. You have an A, right? And there is a next state which is not A, the initial state again, and that state has the possibility to move to A and then exists not A. But you see, I need a very long formula to distinguish this thing. And that's the key thing of this proof, that you cannot distinguish the two transition systems by a formula up to a certain length. Good. But that means they fulfill the same CTL formulas of a certain length. And in the end, this proves a sketch that you cannot express this formula in terms of LTL, in terms of CTL. Good. How about this? For all eventually A and there exists next A is equivalent to this formula. Yeah. The first thing to make a guess is that you need to, the way to think about this is in terms of a picture, right? You first try to, if you ask to answer this question, the first thing you do is you try to draw a picture. So you say, what's the formula on the left expressing? It's something expressing that for all paths, take a path, eventually you get to an A state, and this has an A successor, for instance here. No? This can be a not A successor, this can be a not A successor, this is all fine. Is equivalent that eventually A and next A? I wouldn't say so, right? It's not the case that every path reaches an A state and its next successor will be A, because take this path, and it will reach A, but it could be the case that the next thing on the same path is not A, but there is a possibility to move to an A state, right? That would satisfy the CTL formula, but not the LTL formula. So my gut feeling is that this cannot be true. No? That's the way I would look at these problems. First try to get some kind of intuition. Could this be true or not? No, this is not the case. And now the problem is to find a counterexample, and this is a counterexample. I think the colors are clear. This doesn't satisfy eventually A and next A because I can move here to the right. This is an A state, but the next state is not A. So that's exactly the path I showed you. But it satisfies for all paths. Eventually I go to a blue state, and that blue state has as direct successor a blue state. What was the counterexample here? The counterexample here was moving to the right. So let's move to the right. Yeah, moving to the left is obviously not a problem, I hope. So moving to the right. This means this path should fulfill. Eventually I reach a blue state. Okay, that's here because I reside in this state. And that state has a blue successor. Yes, it has this blue successor. Yeah. Although I move to the right, the successor that is existing going on the left is actually ensuring that this formula holds. Yeah? And that's the whole thing, that mentally in these trees you always, I mean, most of the time you have to reason about a path, but then also about the options that you didn't take along that path. Yeah. And that's why people like Moshe Vadi, Leslie Lamport, they are big fans of the linear time thing, because they say this is way too complicated. Yeah. So that was this battle that I mentioned in the beginning, linear time versus branching time. People think, oh, this is way too complicated. Because I have to reason about things, about paths that I'm not taking, but they're existing somewhere. Yeah. Good. Okay, so this is the formal argument. Same reasoning, but now formally. So again, our reason inside out exists next A is satisfied by the two blue states because they both have a blue successor. And then the set of states satisfying this formula, both the initial state and that state satisfy the formula. And therefore, in particular, the transition system, because of the initial state, satisfies the formula. I think the argument was clear. For every Büchi automaton, there is a CTL formula such that for all transition systems, the transition system satisfies the CTL formula if and only if all traces of it are included in the language of the Büchi automaton. This cannot be true. Büchi automaton, LTL and CTL are incomparable. This would be very surprising if this would hold. Indeed, this is wrong. Take a Büchi automaton for an LTL formula that we cannot express. This is the LTL formula that we already know. We cannot express this in CTL. So this is my Büchi automaton that accepts this, exactly this language, but there is no CTL formula that satisfies this thing. Then you can juggle around with negations. If this is a CTL formula and that's an LTL formula that is equivalent to it, can I then put a negation on the left-hand side and then put a negation on the right-hand side that something get equivalent? No way. Yeah. Be careful. We just have seen actually the example. Take this box eventually, delete the quantifiers, we get this LTL formula, and we know they are equivalent. Now take the negations. Yeah? So take in particular the negation of this formula. Yeah? So what happens if I take a negation of that formula? Well, this negation becomes something of the form eventually box not A, and we have seen eventually box something cannot be expressed in CTL. So this is the wrong conclusion. Message, be careful with negations. And then you can play all kind of other quizzes. S satisfies there exists a path such that all states along that path have a path that eventually leads to A. Yeah. There is a path such that this path has infinitely many A's. What's your feeling about this? This doubly nested existential quantification is a bit worrying, right? Perhaps. Any suggestions?
If in the tree view you have like one path that itself does not have any A's?
No A's, right?
This whole path.
Box, no A, right?
But every node on that path has a branch which leads to a single A. Then this.
And this goes to an A state, right?
Yeah. And this like for every node.
And this one also has somewhere that I can move to an A state, right? And the same here, right?
Exactly.
Yeah.
And this satisfies all CTL formula, but the path itself, like none of these paths has infinite.
Exactly. None of these paths has infinitely of an A. Yeah? So if you are confronted with these kind of questions, then first try to think in terms of these computation trees and try to even draw such a simple intuitive picture and then try to get a feeling about this. So So this is wrong, and here is a counterexample. This transition system satisfies this formula. There exists a path such that it's always the case that there exists eventually A. Same trick as was just suggested. Take a path, here for instance, right, that never visits an A state. The A state is in the middle. Yeah. But for all possible states here, for S, there is a path that eventually goes to A. Yeah. So that's the case. But there is no path such that infinitely often you get an A, because you can only visit this state at most once, but definitely not infinitely often. Good. I'm not sure whether the door is open. Now I have swapped the two modalities. There exists a path such that eventually I get to a state where there exists a path which is completely A. Yeah. So in terms of a picture, there exists a path, this one, such that eventually, maybe here, I get to a point such that from there on there exists a path which is completely satisfying A. That means that this state itself has to satisfy A. No? And there is a possibility, maybe not this possibility, but it might be the case that you can move here, go to an A state, A state, A state, and this is completely A. Yeah? This is box A. That's the situation. Now the statement is, if and only if there is a path such that from some point on always A holds. Doesn't look too bad, right? Because now I can of course take basically this path up to here and from there continue. Yeah? And this is a path that's from some point on is only blue. Yeah? So this doesn't look too unreasonable, and that's indeed correct. And now this is again juggling with negations. This double existential quantification is actually negation, is equivalent to a negated formula with a universal quantification where the box and diamond are swapped, yeah, and then with not A. So we have that a state satisfies this existential formula if and only if it doesn't satisfy this part. But that's equivalent, as we know. This formula is equivalent to box eventually not A. And now I can push in a negation again. That means that that this formula is the same as not eventually box A. And that means that S violates this formula. And that means that there is a path pi satisfying this property. Good. Yeah, more of those quizzes. There is an LTL formula where this LTL formula is equivalent to not existentially, that doesn't exist a path so that eventually I get to a point, so this is the negation of this thing. It is not the case that there is a path that eventually gets to a point from which on there is always such a path. This is also correct, again juggling with negations. So this formula, I mean, you can push the negation inside, so that becomes a universal quantification, that becomes a box, that becomes a universal quantification, that becomes a diamond, that becomes not A. That's what is written down on the right-hand side. And now we know that this is a shape that we are familiar with. This means infinitely often not A, so that's equivalent to infinitely often not A. But that's exactly what we wanted. Good. There are more of those quizzes. I don't think that's a big deal. But there is one important point that I would like to show. Now, that is this one. If T1 and T2 are trace equivalent, so every trace T1 can exhibit, T2 can exhibit, and vice versa, then for all CTL formulas, T1 satisfies phi if and only if T2 satisfies phi. Good. This is wrong. Why is this wrong? The intuition being that trace equivalence says something about sequences. It doesn't say something about the potential branching at points. Yeah? This was all fine for LTL. If you replace this by LTL, this is a completely true statement. But for CTL it's not. And the way to view that is the following. So here are two transition systems. This is one transition system with two initial states, two disconnected parts. And this is a transition system where you have this branching. I hope we agree that T1 and T2 have the same traces. They satisfy the same LTL formulas. But this one, you can express the fact that there is a possibility that you can have an A successor and you have a B successor. You cannot express this in LTL, but you can express this in CTL. And that's the following formula. There exists a next state which is satisfying A, and there exists a next state which satisfies B. This, of course, is not satisfied by this thing, because there is no state that has both an A and a B successor, but it's satisfied by this state because it has both an A and both a B. So what does this mean? It means that trace equivalence is incompatible to CTL. Trace equivalence is compatible to LTL. Linear time, linear sequences, traces. Yeah, but for branching logics, like CTL, but like CTL star, like model mu calculus, whatever, trace equivalent is not the right equivalence. Yeah. Good. That's it for today. Friday, CTL model checking.